Today, we will explore the concept of multiplexing, which is loosely defined as to send multiple signals on a single channel. You could also call this simultaneous communication. In block diagram form, that might look something like this. Our three independent but simultaneous conversations are all brought together into a mux. The output of the mux is sent on a single channel, for example, a cable or fiber or over the air. On the other side, we'll find a demux or a demultiplexer, which is used to recover the three independent signals. There are many different types of multiplexing. Including frequency division multiplexing, which we'll abbreviate as FDM. There's time division multiplexing, which we'll abbreviate as TDM. Code division multiplexing, CDM. Waveform division multiplexing, which is, of course, WDM. And finally, there is spatial multiplexing. As an analogy for the different types of multiplexing, you might want to consider people talking in a room. Frequency division multiplexing would break the spectrum into pieces. You might have the low speaking voices here and the high speaking voices here. And that would be breaking the spectrum. Let's make a little note here. So we split spectrum. Time division multiplexing splits the time domain. You might have one person speaking here. We'll call that person A. Sometime later, person B speaks, then C, and maybe back to A. So we're splitting time. Or you could say take turns talking. Next is CDM, code division multiplexing. Personally, I find this one rather interesting because we have multiple people speaking at the same time. Right, so this is a time thing, but they're all speaking a different language. And it's up to you to interpret the language or to filter out the particular language. For example, if folks are speaking in Spanish and folks are simultaneously speaking in English, your filter, which is to say your brain, can filter one of those conversations from the other. This analogy gets a little silly when we start to talk about waveform division multiplexing, because we don't naturally have a way of doing that. However, you can imagine people in a room, each with different colored flashlights signaling to each other. So the blue light might mean one thing and the green light might mean another. So waveform division multiplexing is typically associated with fiber optics. That brings us to spatial multiplexing, which is perhaps the one we're most familiar with because small groups will break off to different corners of the room. And as long as we each keep our voices relatively low, all can communicate effectively. You'll see this with radio stations as you travel across the country, because there are many radio stations that share the same frequency. However, they are not in the same parts of the country, therefore their signals will not interfere with each other. Let's go ahead and take a few minutes to look at specific examples. For FDM, we could consider the old school television. In the frequency domain, each channel is assigned a specific location. For each individual channel, we could talk about the frequency domain. For example, channel 4 would have an F2 and an F1, so the bandwidth of channel 4 is F2 minus F1. That bandwidth is very important in FDM because we have to maintain each channel to a certain location. For example, it would be very bad if channel 4 started expanding out and colliding with channel 5, or if it started colliding with channel 3. That type of interference is not welcome. So we must be very particular with our bandwidth. And like we said, each channel has a specific bandwidth. As a specific example, we could talk about FM broadcasting. The FCC has allocated a spectrum between 87.8 and 108 megahertz, with each individual station having a 200 kilohertz bandwidth. Knowing this, we can calculate the total number of stations, which works out to be about 101 individual stations. Obviously, there are more than 101 stations across America. However, it is the spatial multiplexing that allows us to reuse frequencies. For example, a station in northern Maine will not interfere with a station here in Connecticut. Speaking of FM radio, you'll find that it has a very interesting history. Originally, FM, as we know it, was in the 42 to 50 megahertz band. And then some things happened, and it moved to 87.8 to 108 as we know it. If you're curious what happened, it's actually a fascinating story. You can read about it in a book called Empire of the Air. I think you can also watch a documentary that was made by PBS. At any rate, it's an interesting history where you'll learn about Armstrong, who is the inventor of FM radio, and the rivalry between the head of RCA, Sarnoff, who adopted FM into television. The reason I bring this up is that FM has changed over time. Originally, the bandwidth of FM was something like this. It went from 50 hertz to about 15 kilohertz, which was fine in 1949 at a time before stereo. Right? You could think of this as the left plus right information was contained within that original band. To add stereo, they added a few things. Here is a 19 kilohertz pilot tone. Then we do some frequency division multiplexing where we add a left minus right channel here, centered at 38 kilohertz. Here's the other image of it. You could think of this as the upper and lower sideband, which is centered at this point here. It's at 38 kilohertz. Remember, this was our original 1949 technology. By the mid-60s, certainly the early 70s, we had stereo information. But we're not done yet. We can keep on with this frequency division multiplexing and add something called RDS. Some of you may be familiar with that. If you have a car, you see that as the now playing. This is a digital data stream. And if you're curious, it uses a 57 kilohertz subcarrier. Occasionally, you'll see yet another piece of information, frequency division multiplexed in the FM signal, and that is the subsidiary commission's authorization. There you can find things like background music, reading services, maybe foreign language services, or in some cases it'll be more digital data transmission. Anyway, this is an example of frequency division multiplexing. We have multiple subcarriers. For example, RDS may be centered there, SCA is centered there. Stereo is centered at 38 kilohertz. It has this 19 kilohertz pilot tone to help with the demodulation, and of course you have the original left plus right. All of this would be considered baseband, and that is the signal that gets sent to the modulator. When the modulator is finished, we have an FM station with a 200 kilohertz bandwidth. Moving on, let's look at time division multiplexing. To do that, we're going to consider a mechanical analogy. Similar to the cap and rotor that you might find in your car. We have this member here, which is rotating. And over here on the receive side, we have the same member that is rotating. So this is the transmitter, and this is the receiver. Again, both have rotating switches. Each segment corresponds to a particular input. We'll let this be signal 4, signal 3, signal 2, signal 1, and we'll call this a special one called sync. We have the same thing on this side. This will be the sync output. This is signal 4, signal 3, signal 2, and signal 1. As shown, the transmitter is currently sending signal 3 on the channel. That is being delivered to output 3. Sometime later, the mechanism will have advanced and is now transmitting signal number 4, which is delivered on the other side as signal number 4. As each switch rotates, you can see that the channels are sent sequentially, or serially would be the technical term. In the time domain, we end up with something that looks like this. We send signal 1, we send signal 2, signal 3, signal 4, and then, perhaps at a higher amplitude, we send the sync pulse. Only to start all over again with signal 1. By the way, this period of time here is known as a frame. frame is essentially one revolution of this switch mechanism. Now, of course, we don't actually use mechanical switches. We use digital or analog methods so that we don't have all the problems associated with mechanical switches. But one problem does remain, and that is, how do we synchronize the transmitter and the receiver? For example, it would be very bad if the transmitter was sending S1, but the receiver was placing that output on the S4 channel. You might not like that if you're having a phone conversation, because all of a sudden, if you're talking to your mother, you might actually be talking to a complete stranger. That would be a system out of synchronization. Know that there are many different ways to solve this problem. One method, an analog method suggested here, is to send a sync pulse, which has a much higher amplitude than the other signals. That would allow it to be easily detected, and the receiver would automatically move to that zero position every time the sync pulse was received. Speaking of old and sync pulses, some of you might remember analog TV. You may even remember adjusting something called the vertical hold and the horizontal hold. Or at the very least, hitting the TV when the picture seemed to roll or to lose synchronization. Now, those old TVs worked something like this. In fact, it was like plowing a field. You had an electron beam that would scan across the screen, one line at a time. In the time domain, we could actually look at the signal for a single sweep. It would look something like this. This is called the sync pulse. And then you would have the various video signal that would ride on top of that, only to be met once again with a sync pulse. It was these sync pulses that kept the picture where it was supposed to be. However, from time to time, they got out of whack, and if they did, you had to adjust the vertical hold or the horizontal hold to adjust the levels so that the TV would actually recognize those sync pulses. Well, that about wraps things up for today. I will make one last comment, and that is we will come back to talk about time division multiplexing another day. Specifically, we're going to show how it's used in computers, with an emphasis on something called time division multiple access, a concept that is fundamental to the operation of Ethernet.